you have a data segment contains all the global variables. You may also have a stack if you want to make function call. So where does this memory resides, like the code or the data or the stack? So after you construct a assembly code, you compile it, not compile it, you assemble it to machine code. And either manually or automatically, the tool chain will lay out the memory. Say code be somewhere here, data be somewhere here, stack will there. And this allows you to run one program, one sequential program. See, when the machine starts running, it jumps to the entry point to the code you've written and start executing line by line or instruction by instruction. So what if you want to run multiple programs on the machine? See, two programs, they run different code. They use different global variables or data. And they have a different call stack. And they run interleaved. So where should we put these memories in the physical memory space? We have to lay out like this in some kind of interleaved fashion. And someone must need to maintain these interleaved memory organization. The code that used to manage this is traditionally called a layout manager, memory layout manager. And these are traditionally called segment of programs. So now there's a problem. Can you arbitrarily lay out these code segments? For example, can I move this code of program 1 a little bit lower, give it another starting address? Is this possible? If I move it, does this program still work? So how does a program use the memory? They either access a memory cell to read the content or write something on the cell, or the program can jump to somewhere. So when you write a variable in C programming language, you use a variable identifier, right? But how about assembly language or even machine code? You have no identifiers, right? What you only have is the address. Similarly, you can go to a label in C program, call a function, but what happened in bare metal? You don't have any labels, you don't have any function names. What they are doing is jump to some address, right? So these addresses are binded inside the code with the variable names, function names, these kind of stuff. What if I move this piece of code somewhere else? Does this name binding still effective, or does it still work? Consider I call a function. Function name is func. I call this function. So this function is binding to an entry address of 200. Now, consider this is a memory layout. Here is a function. The code that function actually execute. So this address is 200. Can I move this piece of code somewhere? Say I move it to a place starting at 50. Ideally, this function should still work as long as you fix every piece of code that calls it, right? You need to change this to call function. This call function would be some kind of a jump with some context saving jump to the address 200 in hardware or assembly level, right? So as long as you resolve all these kind of name binding to address from 200 to 50, this piece of code should still work, right? However, can you resolve it on the fly? No, you can't. These addresses are binded with names at compile time. So now we are facing a big problem. After I write a program, after I compile it, and it must be loaded somewhere, a predefined place. No one can move it in the memory. What if I want to move? What if I want to run multiple pieces of code in the same machine? Okay, now these programmers must communicate with each other and talk about, okay, I'm going to use 200. Then you cannot use 200 anymore. You can only use 50. And you cannot step over 200, right? Can we host a forum to let all the programs talk with each other and resolve this kind of an address confliction? How many programs you are going to run? Potentially infinite many, right? So this is not going to work. We need some way to either dynamically bind the names with the address to allow the physical memory to be kind of flexible, or change this address on the fly. Now I have another proposal. How about, say, don't use 200. You use a base plus 200. And when I compile the code, I put this 200 with the instruction. But every address comes out from the CPU must be translated by some kind of memory management unit, piece of hardware, to resolve this by adding a base. As long as I can set up the base of each segment, then if I move this piece of code from 200 to 50, I just need to change the base. For example, at the beginning, the base would be 0 when the code is located at 200. When I move it to 50, how about I change this base to minus 150? This piece of code now still works because every address, the offset is hard-coded with the instruction, but this base can be changed. I can use a pair of a register to define, okay, this segment has base, has length, right? So how many segments do you have? Just a few, right? Maybe if you want to run multiple programs, it might be multiple of a few segments. Kind of a clever idea, and it's widely used in the 1970s, 1980s. So this is called segment-based memory management. And this allows another clever idea of what if, can I run a lot of program with a very, very insufficient amount of memory? See, I want to run two programs. This program requires like 10 megabytes. This requires 20 megabytes. But I only have 10 megabytes. Can I still run these two programs? Maybe I can swap out some of the segment if it is not accessed or it is not run at the slice of time. And if I need to run this piece of code, I can swap something out to the space and grab those segments in and relocate it somewhere. Segment-based memory management facilitates this kind of swapping with a unit size of a segment. However, the segment can be big or small, usually very, very big. And segment-based memory management are facing a problem called external fragmentation. Say, I have a physical memory of 100 megabytes. I have three programs. Each program requires 50 megabytes. So ideally, I can fit two programs in the memory and run them in parallel. But if the first program is laid out in the memory in a rather scattered way, you have a lot of chunks of memory that is free, but it's not continuous. If it is continuous, can you load a continuous segment from a disk into several discrete parts? Can you do that? Maybe you can, but after it's loaded, is this still working? Is this addresses inside this segment still resolvable? No, because this segment must start with a base and a continuous chunk of memory. So that is called an external fragmentation problem. So usually when a machine starts running for a small amount of time, you will immediately see all the memories would be segmented into pieces. There will be very, very small chances to find a whole chunk of a continuous free memory space to allow you to load some segment or another new program. So how to resolve these kind of segmentation problem? One way, abandon the segmentation. Another way is kind of tricky. How about make the segments smaller? Or now a code segment would have maybe 1,000 sub-segments. So these sub-segments each have a individual base and this kind of layout registers to allow you to move it scattered somewhere. And how about make these small sub-segments always the same size? Right? If every sub-segment is only 1K, then you have 100K memory. You can scatter them in 100 places, like buckets with potatoes. You always put potatoes in the bucket. So after we follow this way, these sub-segments are not called sub-segments anymore. They are called page. And now, translating a memory address from the code to the actual physical memory address needs a kind of a similar adding a base kind of a strategy. However, this base is a per page base. And this translation can be put into a table for each virtual memory, a chunk of a virtual memory address with the same size as the sub-segments I mentioned, or the page size. You need a base register, right? This is one translation entry. And for all the virtual memory pages, each of them needs a translation entry. This translation entry collectively called page table. Okay, so now let's summarize why we need memory management. So memory management allows us to run multiple programs sharing the physical memory. And each program have the whole virtual memory address space and use the memory at any place. So let's explain that a little bit. Previously, we say that if you use a segment-based memory management, you need to change the address or changes how to interpret these address in the programs, right? But you still need to worry about where these programs must be loaded, because all the programs use the same set of translation tables, translating from segments to physical memory. How about we give each program an independent translation table, so that each independent program would say, okay, I think I have the whole piece of the physical memory owned by myself. No one's using that. I'm gonna using a part of them, like this is code, this is data, and these are the stats. And these memory pages will be translated to physical memory. And another program also think it uses it owns the whole virtual memory address space, or all the memory, that it can translate its segments into different places, as long as these translations are valid and well maintained, and they don't influence with each other, then different pieces of memory used by different programs will never interrupt or collide. And in this way, each process is considered to have a independent virtual memory address space. They can put code anywhere as it wants, and these entry address or the go-to labels, name bindings, they have nothing related to other program or the memory management layout. And so who maintains this memory mapping? Obviously can be some process, right? So the kernel maintains this memory mapping, and the mapping granularity is based on page. We map each page, a virtual page, to a physical page. And now we got a problem. So every time I need to go to some label in the code or access a global variable, this address would need to be translated using the page table. Where is the page table? Previously, one mentioned segment-based memory management. You can store the base and length of each segment in 2 registers. Registers are quite close to CPU, and they are only a few segments. For example, I can see there are only a dozen or these kind of numbers of the segments. So we can put all these registers inside the CPU. Now you have page, and page translations usually the translation entries is much larger than a few segments, right? Consider I have 4 GB of virtual memory address space, and each page is 4 KB. How many translations do I need to maintain at most? So 4 GB divided by 4 KB is roughly 1 million. So 1 million translations. Each translation translates 1 virtual page to 1 physical page. How long is it? Must be the same size as the address of a physical memory, right? So how many memory do we need for just storing these page table entries? We need 1 million entries. Each entry is a 4 byte, which is same as a address bits, right? So we need 4 megabytes to just store the page tables. Where should it store? Can we store it in CPU? Okay, you can make a big cache to store the 4 megabyte, but this is only for one process. How many processes you are running in project 2? Say the fork bomb. How many processes you started? Nearly 1,000, right? So can you put 1,000 copies of address translation tables in CPU? You can't. So it must be put inside the memory, physical memory. Now the problem is, every time I need to figure out where is the physical address corresponding to a virtual address, I need to first go to the physical memory to check the page table translation, and then grab the page table translation, and use that translation to get a physical memory address. So one memory access would be 2 accesses. To speed up this, the CPU has a small cache, just exclusively used for caching these translations. The cache is called TLV. Another benefit of using translation entries or the page table entries is memory can be protected. I can allocate a few bits saying this translation, or this translation means the physical page is read only, you cannot write it. Or this translation belongs to some process, other process cannot access it. So this kind of memory protection can be applied on the per page granularity instead of per segment granularity. Now let's have a look at an example of translating virtual address to physical addresses. Here the virtual address is a 2 gigabyte virtual address space from all 0 to this number. It's 2 gigabyte. And the physical address is address space is much smaller. And you can see each individual virtual page will be translated to a physical page. And some of the pages are translated, some of them are not. And some region of the memory virtual address space is not mapped at all, which means there is no such translation, valid translation. This is some kind of a memory hole. What if you access some address lies in the hole? What will happen? What happened? You got a page fault, right? When you're accessing the holes, the kernel will tell you there's nothing there. Either kernel allocate a page and map it for you on the fly, or the kernel just say, you are not playing with the rules. I just not allow you to run anymore. The kernel will terminate it and print out a segment fault, right? So why it is called segment fault? You accessed invalid segment. So these numbers are virtual addresses, and these are the physical addresses. And for these segments in the virtual address space of a process, we call them virtual memory area, formally. Informally, segment. And each virtual page is translated to a physical page using page table. Here is the process address space in Linux. So this is a structure that represents the whole virtual address space of a process. Each process has its own independent virtual address space. And how about thread? You can run multiple threads in the process. Are they holding different virtual address space or not? Right, they share a whole virtual address space so that you can access global variables among different threads, right? That's the difference between thread and process.
Is there ever a situation where they won't happen? Where you won't have one type of thread in another? Because we've been working with K-thread, for example.
Yeah, good question.
And different threads or K-threads won't work for something else, right?
Yeah, good question. So each process contains at least one thread, right? But how about the K-thread, the kernel thread? The kernel thread does not belong to any user process, right? So does it have any virtual address space? Technically, yes. The virtual address space only lies in the kernel. It does not have a user address space. In Linux kernel, the lower three in 32-bit Linux, the lower 3 GB virtual address space is allocated to user programs. The upper 1 GB is allocated to the kernel. So for kernel thread, they only reside in the kernel. They can only access the addresses above the 3G. And for user space, you have a user code that runs in the lower 3G, but you cannot access anything above 3G, which is a kernel, which is where kernel resides. And this process address space descriptor is called an struct, memory management struct. This per process data structure can be found by the task struct / point to mm. And sometimes you'll find this pointers null, like the kernel thread. Let's have a look at the few fields of them. First, the memory map. This memory map is a linked list of memory areas. What is memory area? These segments. So for each of these segments, there's data structure called VM area struct, describing one of the segments. And the struct has a linked list, links all of these. And you also want to search these segments very fast. For example, I give you an address. You tell me where the address resides, either in the whole or in some valid memory area. So kernel uses a red-black tree to index the memory virtual memory area. The root of this red-black tree is here, the MMRB. And also, to translate pages, you need a pointer points to the page table. Right? What is this pointer called? It's usually some kind of a global directory pointer. In x86 or ARM, there's a hardware register that allows you to put this pointer into a hardware register, so that the hardware register uses this pointer to find all the page table entries. When you're switching from one process to another process, you change the content of this register. On x86, it's a CR3 register. On ARM, it's called TBBA and TBBI register. We will see it later. So this is a pointer to all the page tables. Or if you use multiple level of page tables, it points to the top level one. And also, when you are traversing the page tables, traversing the page table entries, you don't want the other one to interrupt you. Here's a spin log that protects the page tables of one memory and one process address space. Also, the process address space contains some common values to denote where the code segment starts, where does the data segment start, where is this is usually called BSS, block start by symbol, which is uninitialized global variables, and also the argument environment. This is a very simplified version of a struct. If you go through the kernel, this is a huge struct. And also for each of the virtual memory area, it contains a few interesting fields like the start, end, and the access permissions. For example, what is the access permission for text segment? The usual access permission for text segment. So what are the possible access permissions? It could be read, write, or execute. So what is the permission for text segment? you can definitely read, right? And you can execute. Are you allowed to write? Are you allowed to modify the code? Nowadays, no. Back in the 1970s, back in the early ages, you can write self-modifying code. See, the code starts running and modifies its own instructions. Yeah, kind of weird, right?
Wouldn't that get a lot of errors though?
If you carefully write this piece of code, it can run legally. Yeah. But nowadays, we don't allow anyone to modify the text. And what is access permission for data? Yeah, read and write, right? So usually, memory place allows to store global verbs must be allowed to write. But can you execute in data segment? Usually you cannot. However, in old processors, there's no way to allow to deny execution from a certain place. Also for stack, the permission is similar as data. Have you heard about the stack overflow attack? So if you receive a few data bytes from the network or from user input, where it is stored, usually in local variables, right? Where is local variable stored? Stack, right? If the malicious attacker inject a few code in the stack and carefully modify your stack frame to ask the program to jump to somewhere here and start running it, then you are running the injected malicious code. This is called a stack overflow attack. Why does this attack work? Why it can happen? Because old processors cannot deny execution of code in stack. Newer processors have these features. We'll see soon. Okay, for virtual memory area, that's basically it. So how does this access permission is implemented? I see the kernel say you're not allowed to read or write this piece of code, but the program can still read or write using assembly instructions. How is this happen? How can you deny read or write? This requires hardware assistance. There's 2 bits in the page table entries. 1 bit for read-write permissions. Another bit is for execution permission nowadays. Usually not present there in the old processor. So the operating kernel code can change this bit, and the hardware will interpret this bit. For example, if this bit is 1, it allows the hardware to write into this address or write into this page. If it's 0, then you triggered a protection exception, usually like an interrupt. And this exception traps into the kernel, and the kernel will figure out what the user space program is doing. Maybe you are accessing some memory spaces and are not allowed to access, or you are doing something valid, like I allocate a piece of memory, and this piece of memory is mapped on demand, and just using it. So for any program, you can read out the virtual memory area, all the segments, by prog file system. If you go to prog, PID, and maps, you can see these segments. For example, I wrote a very simple Hello World program and launch it with PID this, and I can print out the memory maps of the Hello World program. You can see there are a few segments with read, not write, but execute permission. This is a text or the code segment. And this is the starting address, and this is the end address of the code segment. And also there's a place that allows you read, not write, and not execute. This is a constant pool or a segment that only stores literals or constants. Also, there's a segment with a this is not this is constant pool, and also a read, write, and not execute. This is a data segment. Also here's the stack. The stack usually grows from top address to from a high address to low address. So it is usually placed in a quite high place just below the 3G. Beside my program, there are a few segments for the dynamic linking libraries. For example, the C library and the linker itself. So the linker, this piece of code allows you to dynamically load a piece of code and link it to your memory address space. So after we mentioned about the virtual memory, next let's have a look at physical memory. So we mentioned for 4 GB memory, virtual memory space, you need to translate the valid pages to the physical memories. So how large is the physical memory? 4 GB? Or some value else? There's no restriction for that memory size, right? You can purchase 16 GB if you want, right? There's no restriction saying that you have to use a certain amount of physical memory. The more physical memory you have, the more performance you get, right? However, on 32-bit machine, you can only use 4 GB memory, because every address will eventually go through the physical memory, and the address is only 32 bits, 2 to the power of 32, 4 GB. If you really have a more than 4 GB memory, you can use 64-bit machine, or use a kind of a tricky strategy called a physical memory extension, for these kind of strategy to translate a 32-bit address in virtual address to some like 48 or 36-bit in physical address. For each page, Linux uses a structure to manage it, the struct page. And for example, if I have 4 GB of physical memory, how many of these structure do I have? Quite a few, right? More than 1 million, right? So each these kind of structure occupies a handful of bytes, roughly 40 or 44 bytes in different platforms. So let's have a look at what does this structure contains. It contains a flags telling about the permissions or the attributes associated to this page. We'll see it soon. And a counter. So we see the virtual page can be mapped to a physical page. How about I map 2 virtual pages to the same physical page? Is this allowed? Yes, it is. What is the benefit of mapping 2 virtual pages to the same physical page? Previously, we heavily emphasized isolation of different processes. Now, why I just want to map the two pages into the same physical page? Note that
Save space.
save space. Good idea. If these two pages are just read-only, it contains a bunch of constants, strings. How about I map them to the same place to save physical memory? So what is read-only? Code, right? What kind of code can be shared between or among various processes? C library or these kind of library, right? So that's one reason I want to map different virtual pages to the same physical page. What are the other reasons? The process can communicate with each other using a shared memory. Why using shared memory or not copy to the kernel and copy from the kernel to the other user space? Because using shared memory is efficient. So this count, this map count, it denotes how many copies of mapping is there for a physical page. And this mapping is a mapping field is an address space associated if the physical page is in page cache. Now, let's introduce a little bit about page cache. So we say a physical page can be used or not used, which is free, right? If it is used, it is either mapped into some address space, right? It is mapped to a process user address space or mapped into the kernel's address space, or it can be used as a cache. For what? For files or other block devices. Why do we need this kind of cache? Consider every time you open a file, you go to the disk directly. That's the intuitive idea, right? But it is slow because traditionally disk is mechanical. It has ARM with a bunch of disks. And you need to move the ARM using a tiny motor to a track and read out the magnetic information and translate to binary digits. So this is slow. But if you cache a portion of a disk inside the memory, consider memory is big enough, then it significantly improves the performance when you read and write files. So that's why we need a page cache. And that's why we need physical pages to be sitting in the page cache instead of mapping some memory address space. And also, we are talking about how to use pages, map pages, allocating pages for cache. So there's a ton of a reason to ask for pages. Is there a way to return pages? What if the memory is insufficient of physical pages? How do you handle this situation? This feature is generally collected called a page reclaim. You reclaim used pages and free these pages by either write the content of the page to somewhere, like the disk, or just discard it. For example, the page cache. The cache is the files. So page reclaim needs a maintenance list to figure out which pages are used frequently and which pages are not. You always want to reclaim the infrequently used pages, right? So for example, if I cache the file and that I use quite frequently, and I reclaim the page for the cache, what will happen? it will affect your performance unfavorably, right? Or if I map a page in the virtual address space, but I need to frequently access it. However, I want to reclaim some memory. I swipe it out, write the content to the disk, and free this physical page. What will happen? Next time I access it, it must be grabbed from disk into the memory again. So if you are insufficient, really insufficient memory, and a lot of these kind of things happen, what is called? Consider I'm accessing like 100 pages, but my physical memory only contains 80 pages. I'm accessing all the 100 pages. Then the operating system kernel must swipe some page out, swipe some page in quite frequently. This is called thrashing. And that's the topic you need to resolve in project 3. Okay, so we mentioned previously about how to map physical virtual pages to physical pages using page tables. So page table contains page table is basically an array. It maps the array index is virtual pages, and the array content is physical pages. And the number of virtual pages and physical pages are frequently called virtual frame number and physical frame number, VFN and PFN. Here, for example, the first virtual page is mapped to the second physical page. Here, the second virtual page, this is not the second, the third physical page, because array index starts from 0. Also, the second virtual page is mapped to the fourth physical page. And this page table is stored in the memory. But we previously mentioned, to map a 4 GB virtual memory space, you need 1 million entries, right? This is definitely not sufficient. So we invented a 2-level page table translation. See, this is a example of a 2-level page table translation on x86 machine, 32-bit. A linear address is a number, a 32-bit number, and we use the upper portion of this number points to a page directory. This directory contains 1K page directory entries, and each entry points to a page table which contains 1K page table entries. And each page table entry is 32-bit that translates one virtual page to a physical page. Hold on a second. It doesn't seem benefit us at all, because we still need these page table entries, right? We still need 1 million page table entries, right? Not necessary anymore, because some page directory entry will say this part of a page table entry does not exist. For example, I have a 4 GB memory address space. I can see the page directory contains 1K entries. Each translates a 4 MB memory chunk of memory, and it needs another 1K entries of a page table to translate each individual page in the 4 GB. What if I say, no, this 4 GB is totally a whole. No one is mapping that pages. Do I still need this part, this 1K page table entries? not anymore. And for a program of using 4 GB virtual address space, most of the pages are mapped or not mapped. We would say not mapped. For a program uses only a chunk of memory like 10 megabytes or a few kilobytes, most of these page directory entries are saying the page tables are not there. So we saved a lot of spaces by only map the page tables or the chunk of memory we used. For example, if I only use 8 megabyte memory or 10 megabyte memory, there's only 3 entries in my page directory that is valid. It says, okay, this part has memory mapped. All the other parts are missing. And what I need is only 4 set of 1K page tables. 4 set of these 1K page tables. So how many memory do I need? So each 1K page table requires 4 kilobyte because each page table entry is a 4 byte, right? So I only need 12 kilobyte. And in addition, 4 kilobyte for the whole page directory. So this drastically saves the space required to store the page table entries. That's why we invented 2-level page tables. And sometimes you would say 4K page is quite small. Why? What prevents us using a bigger page table size? If you have a 4 megabyte page, and what you need is only, say, 10 bytes, can you say, I only use 10 bytes, leave the remaining part of 4 megabyte page to others? Can you do that? No, because once this page is mapped into your virtual address space, it's yours. No one can own it. Someone can share it, but no one can own it except you. Right? But what if I only use a small chunk of memory? Then this 4 megabyte page is largely wasted. Right? So this is called an internal fragmentation. To prevent this kind of waste, the page size is kind of the smaller the better. As a trade-off of how many page tables entries we use and how severe the internal fragmentation there is, we kind of use a 4K page size. And sometimes, if you really need a large page, like some data-intensive programs, and nowadays the memory is much cheaper than 10 years ago, 20 years ago, we can afford this by providing 4 megabyte page. What is the benefit of providing 4 megabyte page? Say, if I use 4K page size, how many translation entries do I need? 1 million, right? But what if I use 4 megabyte size? How many translation tables I need? Roughly 1K. It doesn't matter, as the translation entries are there in the memory. Memory is big enough, but TLB is not big enough. The translation entry cached in the CPU is not big enough. Right? If my program uses large chunk of memory, I need to cache all these page translations inside the CPU. However, the large this chunk is, the more these cache translation tables entries are there. So using 4 megabyte page, I can save the number of translation caches to make my program run faster. So here's the extended page with 4 megabyte. And now the page directory contains directly the translation instead of another level of translation, page tables. And let's have a look at each page table entry. The page table entry is the content of a page table that actually do the address translation. For example, if I want to translate from a page 10 to a virtual page 10 to physical page 0, then you need to store this 0 somewhere. Or you need to store this 10 and 0 at the same time. So previously we mentioned we use array to store this. For example, the 10th entry of this array is a 0. So this content of 0 is a page table entry. It looks like this on x86. So remember we have a page directory entries as well as page table entries, and we put it here together. See, these are page table entries or page directory entries in 32-bit machines. So, for example, the top level page directory entry will like this if it's present, which means it points to an invalid second level page table. It looks like this. The upper level is used to translate address, which means translate from 10 to 0. Why you only use the upper level? We're translating page 10 to page 0. Page 10, what's the address area of page 10? It's 10 times 4K to 11 times 4K, right? This address is covered by virtual page 10. Okay, I only need to store this 10 or 11. I don't need to store those bits addressing internal page offset. How many bits are there for addressing 4K bytes? 12, right? 12 bits. This 12 bits can be totally omitted because I'm translating one page to another, not translating each individual byte. Right. So here you can see in a page table entry, the lower 12 bits are used for other reasons. The upper 20 bits are used to translate the addresses. And here are a few bits which is interesting. For example, if the last bits of a page table entry is 1, it means, okay, this page is inside memory. If it's 0, it means, no, I do not put this translation there. Also, read-write access bits for here, and user kernel access bit here. There are a few control bits for the cache. For example, for this page, do not cache. Or for this page, using write-through cache policy. And there are two interesting bits. One access bit, one dirty bit. So access bit means if the page is there and the CPU accessed it, the program accessed it, CPU issued an address falls inside this page, then this access bit will be set to 1. Who clears? The kernel or the program. Why do we need this access bit? Without this hardware assistance, do you know when the program accesses some memories? You don't know, but you don't care, right? Who cares? Remember, the kernel has a feature called page reclaim, right? Recycle pages. How can the kernel know some pages are infrequently accessed? See, the kernel, consider I'm the kernel. I clear all the access bit at beginning of every second. Then, at the end of the second, I check whether the access bit is set or not. If it is set, what does it mean? It means this page is accessed in the previous second, right? Then I clear it again. Next second, I will observe, okay, some pages, the access bit are set. I can immediately see, okay, some pages are accessed in the last second. In this way, if I observe for a period of time, I can know some pages are accessed quite frequently. Some pages are not accessed quite frequently. Right? So that's why we need this access bit and a 30 bit. 30 bit means you're not only accessing it, you write something on it. So when I need to synchronize the page cache to the file, if the page cache is not touched or only read in previous second, do I need to write it back? Consider I have file, some chunk of it are cached in the memory, and now I need to close this file. I definitely need to synchronize the cache with the file. If I write something in the cache, right? If I write something in the cache, I do not synchronize it to the file, then I will lost all these written bits. Right? So how do I know some pages are written, some pages are not? Can you use the access bit? No. Access bit tells you the program access it either in read or write. I need to know whether the processor write on it. If the processor write on it, I set up the 30 bit. Note that these 2 bits are set by hardware, not the program. This is an indication of how to manage these pages, whether they should be synchronized back to the file, back to the disk, or back to other devices, or they indicate whether this is quite frequently accessed memories, whether you can reclaim it, or whether you'd better leave it in the memory. So remember, the project 2 says you need to estimate the workspace size. What is workspace size? Consider in the past 1 second, I accessed these in total 10 pages. And in the next 10 seconds, I accessed these 10 pages again. And next second, I did the same thing. For a few minutes, I always access these 10 pages. Now, what is the work size of this program? Work size means the size of memory it accesses in a period of time, frequently. And maybe I would say the only 10 pages I used. I might allocate a huge chunk of memory. I may allocate 1 GB, but only access 10 pages of them. So your job is estimate the work set size, which means estimate the chunk of memory that the process access frequently. How do you estimate this? Can you use the access bit, say I clear all the access bits of all the memory pages of my process at time 0. And after 1 second, I check all the memory pages, see which page are accessed. I mark those access pages and clear the access bit again. Next second, do the statistics again. Go through all the access bit and see which pages are accessed, and mark these pages again. And 1 second after a second, 1 second after a second, I do this statistics every time. And after maybe 10 minutes, I would say, okay, these pages are quite frequently accessed. This is the work set size. Note that hardware, every time the CPU accesses some memory address, the corresponding page table entries, the access bit would be set. It is never cleared by the hardware, but cleared by your program. Another few bits, like the page size, indicates whether it's 4 megabyte page or a 4K page. And here's the x86. And note that Linux also supports a few other architectures like ARM. See, this is ARM v7, 32-bit ARM, the TTB ARM. We previously mentioned that you need a register in processor points to the starting place of the page directory or the starting place of all page tables, right? This register is here, the CR3 register on x86. And on ARM, it is the TTBR0 or TTBR1. And similarly, ARM, the 32-bit ARM use two-level page table strategy, but with different splitting part. So the first level, which is a corresponding, which corresponds to the page directory on x86, is 16 kilobytes instead of 4 kilobytes on x86. It contains more entries. The benefit is on the second level table, you can have less entries. Here, only 256 entries on the second level. We would not go through this in detail, only mention a few things. See, here, the present bit. So if both those two bits are 0 on ARM, on the page table entry of ARM, this means this page is not mapped at all. You will trigger a page fault. And if it's some value else, it means it is mapped. Here, there's an interesting bit called xn. We didn't see this bit on x86 machine. This xn called execute never, which prevents you executing any code in this page. However, this bit is not there on old x86 machine. On new x86 machine, there is a bit called nx, and not shown in these slides. So you will see why the buffer overflow attack harassed the x86 machines for a long time. Lack of this bit. And similarly, ARM has accession permission bits and cache control bit. However, you didn't see a dirty bit and an access bit. These two bits are not present in hardware on ARM, but emulated in software by Linux kernel. So for different architectures, Linux kernels both support the access and dirty these bits. They use different strategies. Okay, let's detour a little bit. So we only mentioned two architectures. They are all 32-bit architectures. However, there are Now, there are 64-bit architectures, and architectures that can support bigger memory with only 32 bits. C. That makes the page table quite complicated. For example, if you are translating 32-bit virtual address to a 40-bit physical address, not 40, 48-bit or 52-bit physical address, you need a 3 level of a page table instead of 2 level. And the page table entries got complicated. And if you use a 64-bit processor, which translates, actually there's a more complication. 64-bit processor only use 48 virtual bits for virtual address, not all the 64. Then you are translating 48-bit to 48 physical bits or 52 physical bits. That's complicates things. You have to use a 4-level page table. And 32-bit ARM also supports similar strategy. And nowadays, there are a ton of different architectures. They have different address splitting schema and different level of paging. Note that these are all defined by the hardware. The software, the Linux kernel, must find a way to cope up with different kind of page table translation schemes. So Linux kernel will take the combination of all these. So let's get back on how Linux translates, how Linux represents page table entries. Linux uses a 4-level page in general. No matter you are running 32-bit Linux or 64-bit Linux, you always have 4-level page table entry. The first level is called global directory. Next is upper directory, then middle directory, and page tables. And the last part is offset, address offset inside the page. So this is a 4-level. They're called PGD, page global directory, PUD, upper directory, PMD, and PT. For 32-bit machines, you only need 2 level. How can you afford the 4-level to 2-level? And I'm wondering how to fold the 4-level to 2-level. Actually, it's easy. Just say upper directory occupies 0 bits, middle directory occupies 0 bits. Right? This literally means the upper directory only contains one entry that points to itself, not point to itself, points to the previous level, right? So in this way, you can always use the same code to walk different levels of page table in Linux. And these page table entries or directory entries are represented by an opaque type called PTT, PMDT, PUDT, and PGDT. They are opaque. You don't know whether it is 32-bit or 64-bit or something else. You don't know the actual bits that are indicating active or dirty or these kind of things. They are opaque to provide a hardware abstraction for the kernel. And how do you access the page table entries? Use the macros and functions provided by the Linux kernel. Similarly, the protection part of the page table entry is also an opaque type. Let's have a look at a few macros that allows you to read, test, and modify page table entries, like PT none or PMD none. These none suffix by none. It means whether the whole entry is 0 or not. Why is testing whether it's all 0, because these page table entries might not be allocated at all. And clear means clear entry. Write all for it. Destroy the map. For example, when your program exits, you need to release all the memory you allocated and destroy your virtual address space. How do you destroy your virtual address space? By zeroing all these page table entries and return the memory allocated to hold this page table entries, not the actual data, the page tables. And you have a set PT, set a given entry to a certain value, or compare whether two values map to the same places with the same access permissions, and check whether it maps to a large page, like whether it's 4 megabyte page or 4 kilobyte page, and see whether it's a bad page table. See, it's not present or no read access. After you have these gadgets to manipulate page table entries, you can also access the bits we mentioned before, like read the dirty bits, read the access bit, clean the dirty bits, clean the access bit. I made a mistake. This is not clean the dirty bits. This is this is clean the dirty bits. This is set the dirty bit, and clear the access bit or set the access bit, and check whether the page table entry is present. So present means if this present bit is 1, means this address is actually mapped to a physical page. If the 0, it means it's not mapped at all. Similarly, if a present bit in the page directory is 0, it means the second level page table is not there. Similarly, for different levels, you will see this bit means the next level is not there. Now, let's briefly talk about how do you estimate the work set size. You need to use this, clean the accessed flag. So write a kernel thread in a module or inside kernel, and this kernel thread will sleep regularly, wake up regularly, like 1 second at a time. And after it wakes up, it will go through all the page table entries of a process and read whether the access bit is 0 or not. After you read it, you clean it. You clear it. It means set it to 0. And next second, you can do this procedure again to see whether these bits, some of the bits are set by these bits of some pages are set by the hardware. You can know which pages are accessed from last second by the hardware, and in this way you can know, roughly estimate the work set size. And kind of we omit something. How do you translate a virtual address to physical address in software? Consider I give you a virtual address. How do you translate to physical address in hardware? In hardware, find the translation entries in TLB, right? If there's no such entry in TLB, there's a piece of hardware that goes through the page global directory. Then, from the page global directory, it finds where the page table entry is, grabs the page table entry, put it into the TLB, and use that entry to translate pages. So the same thing happens in software. you need to go to the page global entry, find the page table entry corresponding to this address, and if you have multiple levels, you go through all these levels until you reach the last level and find the page table entries. And this page table entries indicate the physical memory address. How do you do this? Note that the page table entries are opaque. You don't know what is inside it. But you can manipulate it with kernel macros and functions provided. For example, PGD offset, given a virtual address, given a virtual address space, this MM means the MM struct associated to a task. So given an address space, I can go through the page global directory and returns you the page upper directory entry, right? PGD offset gives you a PUD entry. And you use a PUD offset to obtain a PMD entry. And use the PMD entry, run this, give you a PTE entry. And this PT entry is what you need. Use this PT entry, you can get a page struct which manages a physical page, or use this PT entry to do the address translation to go to that address. So let's have a look at an example of how kernel works the page table. There's a function called follow page that wraps this function, follow page mask. The purpose is look up a page descriptor from a user virtual address. The user virtual address is this parameter. And the VMA is a virtual memory area that contains this address. Note that here we didn't use struct MMF, but use struct VMA. And these flags and the masks control the behavior of how to follow a page. Let's have a look at how this page follow happens. Here it is. Let's start from follow page mask. So at first, follow whether it's a huge. We will ignore all the huge page tables. First, call PGD offset to get a PGD, and use this PGD, check whether it's none, whether this PGD entry is valid or not. Then use this PGD to get a PUD. Oh, I made a mistake previously. PGD offset gives you a PGD entry given the address space, not a PMD entry, a PGD entry. See, you have two levels of page translation. This is the page global directory, and this is the next level. Here in x86, it's the next level, just a page table. You call PGD offset with a address and the MM struct. MM struct denotes where can you find the page global directory, because each individual process contains an individual process address space. Each individual process has a different set of this page global directory. So this gives you where to find this, and this address tells you which entry you are gonna find. So PGD offset gives you a PGD entry. Use this PGD entry and this address, you can get a PUD entry by PUD offset, this function. And check whether it's not there, whether it's huge, and use this PUD entry, you got a PMD entry. And last, use this PMD entry, you got a PT entry. The PT following is not explicitly written here, but in this function, the follow page PT, okay, they happens in several places. So this is common path here. Follow PT entry. So the follow PT entry use the generated use a PMD entry to find a PTE entry, and this PTE entry is what you want. And this function just returns the struct page. And in project 3, you only need to return this PT. So this is basically how kernel walks a page table. Like give you a virtual address, give you an address space. How do you find the physical address? You go through all these levels of page, global directory, upper directory, middle directory, and page table to find the page table entries at the leaf. And this page table tells you which physical pages corresponds to the virtual pages. By the way, how do you get the virtual pages from a virtual address? Say my address is a 0x kind of 1, 2, 3, 1, 2, 3, 4, and my page size is 4 KB. This is a virtual address. This is a page size. How do you get the virtual page frame? So let's have a look at this address, what it contains. Here is only 16-bit. Virtual address 0x1234 with 4K page. And here it is only a 16-bit address. 4K page means the lower 12 bits are used to indicate the offset inside the page. Here, the upper 4-bit, this is the upper 4-bit, 0, 0, 0, 1. And this is the corresponds to 2, 3. Oh, here it is, the binary representation of this address. Hexadecimal 1, 2, 3, 4, something like this. Like this, the upper 4-bit is used to denote the virtual page frame number. Lower 12-bit are the offset inside the bit, inside the page. So this is only a 16-bit address. How about 32-bit? This part grows, but this part does not change because we're still using 4 KB page size. Right? So just mask off the lower 12 bits and shift it, you got the virtual page frame number. And now you have the access bit, and now you know how to walk pages in using this example. And you can also open a kernel thread, sleep, and check each process is, for each process you can access its memory struct. Now you can basically do all the things you need for. You can have all the gadgets you need for project 3. So note that the first task of project 3 is basically implement this follow page function. You don't need to handle all the different behaviors, all the flags, just traverse the page tables. And you don't even need to consider the huge TLB part, the huge page with 4 megabytes size. You can turn it off when compiling kernel, or just ignore it. If you see there's a huge page, consider it's not there, or consider it's not present. The last part is how to verify the virtual address to physical address translation in your code. Here, the Linux kernel export a page map in proc file system. For each processes, it export all the page table entries. So ideally on a 32-bit machine, you will got all the 1 million page table entries. And this file, this page map file, contains a huge array. Each element of the array is a 64-bit value. The lower 0 to 54-bit are the physical page frame number, if the physical page is there. And the index is virtual page number, virtual page frame number. And if the page is swept, you can use the upper bit. The bit 63 denotes whether the page is present. If it is not present, there are many reasons. It can be not mapped at all, or it can be swept. If it's swept, this bit will indicate it is swept out, and the lower bit indicates the lower bits indicates the swept type and swept offset, which means which device it is swept, and what is the offset inside the device, so that you can use this. This is commonly called the swept indicator to retrieve the page swept out on a block device like disk. Here's an example of reading the page map. I started the hello world process and wrote a simple program to read out each entries of this page map. However, I only read out the entries that appears in the virtual memory area. So you know that this page map will give you all the page table entries, even if it is not there. For example, from the address 0, the first entry comes from the address 0 to address 4K. Next entry goes from 4K to 8K. So usually these parts are not mapped at all, but you can still obtain the page table entries just with a present 0 and a swept 0, which means it's not mapped at all. Here I only read out the entries that is mapped. For example, for virtual pages, this number, it maps to physical page, this number. And the last thing, as I mentioned, on a Linux system, usually the lower 3 GB memory is used by the process as a user space program. So the user space program maps all its code, data, and the heap, the places where you call malloc, and the shared libraries and the stack in the lower 3 GB. And the upper 1 GB is managed by the kernel. So if you open the kernel thread, it only accesses this piece of memory. And if you trap into the kernel, say make a system call, you goes to this piece of memory. The code of system call implementation executes there. And this memory is protected by what? By a few bits of the page table entries, right? By the way, a user space program can a user space program access a page table entry and manipulate a few bits there? no, or yes, no, usually no. Why? Consider there's a page table that maps your memory. There's a page table that maps my memory. If I'm allowed to manipulate this page table maps your memory, then I can access your memory, physical memories, right? I can change a few maps, say, okay, your physical page is there. Okay, map to my address space, and I can modify it, right? This breaks the security. So page table entries are exclusively managed by the kernel. No user space program can handle it, can mess with it. So you will soon see in this 1 GB memory space, the kernel virtual memory space, there are a lot of interesting stuffs, like where is the kernel code mapped? Kernel is also a piece of a code, right? Kernel can also allocate memory using kmalloc, right? So where are these? They are all inside 1 GB. There are different types of segments that kernel uses, like map kernel image and the linear mapped address space, and the vmalloc mapped address space, kmap mapped address space, fixed address space, or these kind of stuff. And if you are interested, you can read the Understanding Linux Kernel, that book. It explains something here. We will not talk in detail. Okay, that's it. Thank you. Thank you. Any questions? So let's restate how to solve the project 3 again. For task 1, you are given a virtual address. Then you need to walk the page tables, call the say PGD offset, PUD offset, PMD offset to find the physical addresses corresponding to the virtual address. You actually needs only to reach the PTE, page table entry. And that PTE, return that PTE, that will give you where the physical page frame is. And for task 2, you need to find a process and go through each page table entries of this process using the techniques you've done in task 1. Go through each of the page table entries and clear the access bit and sleep. After a second, wake up, go through all the page table entries, see which one is set by hardware, which one is set by hardware, count the numbers, or even maybe mark these pages, and then clear it and sleep again. And the next second, wake up and go through all these page table entries, see which access bit is set, and count the numbers, or leave a record there. So do it for a few times, maybe for a few seconds. You will know the work set size, because a program usually only access a few pages. And for task the latter half of task 2, it asks you to prevent thrashing. So how thrashing happens? Thrashing happens when the work set size exceeds the physical memory, which means I'm a process. I'm accessing a huge number of physical pages that even exceeds the physical memory size. Now the kernel needs to swap in and swap out pages quite frequently. So how to prevent this thrash? For each process, estimate the work set size. Then add them together. You got the total work set size. If this total work set size exceeds a certain threshold, then you will definitely see thrashing. What kind of threshold it should be? maybe 50% or 80% of the total physical memories. If it reaches 100% of physical memories, then it's definitely gonna see thrashing, because physical memories are also used for page cache or other stuffs. Okay, that's it. Questions?
These slides going to be posted on Blackboard?
Yeah, it'll be posted on Blackboard tonight.
And one other stupid question, I wasn't really here, but what's the reason why the hardware resets all these entries and tells you that your input set value is correct?
The hardware turns a bit from 0 to 1. You set the bit from 1 to 0. Because the hardware won't give you some information. Say the hardware accesses this page. It turns the access bit of this page table entry to 1. Hardware won't give you this information so that you can efficiently manage all these pages.
It's just letting you know there's something there.
Yeah, it let you know hardware accessed that page during the last second. However, you don't know how many times it accesses. Yeah, maybe many times, but it only set from 0 to 1. And it might be frequent or infrequent. But if you regularly check it, you will say, okay, last second it accessed it. Next second it should also access. It would make this kind of a prediction.
Doesn't that whole regime change over time? Wouldn't it access certain things at one time and other things at other times?
Yeah, depends on the memory access pattern of a program. Usually, program has a temporal locality, a spatial locality, which means you always access adjacent memory piece of memories in space and access the same memory region over time, because it's programmed, right? For example, if your program is doing some meaningful things, like adding up numbers, or do some statistics, you are always working on these few data structures you are interested. You are not randomly access memories. By the way, there might be random access patterns. For example, if you have huge hash table, and this huge hash table contains entries of millions of transactions or something else, and you want to check, okay, whether this transaction is, then you need to hash the object and go to the bucket, right? Hash will generally generate random access. So as long as the program is meaningful, doing something, this access pattern can be observed. It's not totally random or totally organized. Okay, I think that's it.
On the Blackboard?
Down the archive. Yep. I think I talked too much.
No.